Welcome! Today we're diving deep into Kubeflow and sharing learnings from over 1,000 Kubeflow pipeline runs. In case it's your first time hearing this term, Kubeflow is an essential open source machine learning framework that covers both the library and runtime aspects. This trusty sidekick is a project of the Cloud Native Computing Foundation and is made up of several components such as notebooks and pipelines. The latter takes the crown for being the most frequently used, and rightly so. Did I mention it's open source? Feel free to dive into the Kubeflow GitHub repositories yourselves. Some fragments, like the pipelines, are separate from the root project, so keep that in mind. When working with Kubeflow pipelines, you'll typically write a pipeline specification in Python and then compile that specification into a Kubeflow JSON or YAML file. Then you can unleash your creation on a wide range of services, be it Amazon Web Services, Google Cloud, or even your homemade Kubernetes cluster. This flexibility of operation is truly a game changer, offering indomitable portability across countless environments, like Google Cloud, without needing any coding prowess. Though we'll focus on GCP as an example in this session, bear in mind that our teachings can easily transfer to any other environment. Before we jump in, let's set the scene. Picture us in a fresh project, eager to enable all the recommended APIs. As those kick into gear, we'll establish a shell environment to build our pipeline and demonstrate some concepts. There, we'll create a directory to develop example pipelines. Right off the bat, we'll reel in an example pipeline. This pipeline, with its couple dozen lines of code, hauls data from Wikipedia on a specific concept and transcribes that as an output artifact. Secondly, there's another component that performs a sort of style or language translation on that Wikipedia data. Picture it as a linguistic pirate, churning out information in unique parlance. All this courtesy of the Claude API and Python SDK, culminating in another artifact. With this moderate-sized pipeline in play, we've got some worthy points to discuss about best practices. But first, let's see the pipeline in action so you can better understand the mechanics before we get into the best practices. Now that we've compiled the pipeline specification ready for Vertex AI, we need to set up a bucket for our pipeline artifacts. If we're dealing with AWS, we'd probably be using S3. But if we're working with a pure Kubernetes-based installation, we'll most likely be using MinIO. Brace yourselves as we dive in to create that bucket. And to be mindful of our budget, we'll stick to a single region bucket, but otherwise we'll keep the defaults. Okay, let's take a trip to the Vertex AI pipelines and get ready to submit our pipeline specification. Now that we've stored the specification in our bucket, we can leverage it within our Kubeflow tips project. We just have to pick our conversation topic. How about Anthropic, the masterminds behind Claude? And just like that, we can commence discussing our best practices. We're juggling two tasks here, gathering some golden nuggets from Wikipedia and transforming that with Claude to recreate the Wikipedia entry as a stylish summary. In between, we also have precious artifacts to consider. Here's a heads up. There exists a sweet spot between modularity, reusability, and computational efficiency. You might feel the urge to employ small, adaptable components with their various tasks when assembling your Kubeflow pipelines. But remember, these many tasks will each prompt a new VM, making it a tad heavy on the computational front. So we could join the Wikipedia and Claude API calls to streamline our pipeline execution and keep it pocket-friendly. This is not as much of an anti-pattern as it may sound. Spinning up a VM just to make a single API call is a bit overkill. And here's our second sage advice. If we gaze upon this Get Wikipedia entry and observe this task, we'll notice that we've unleashed an E2 standard 4 VM on it. Considering it's simply invoking an API to fetch a small amount of text data, this machine is akin to using a cannon to kill a mosquito. Our remedy to this is customizing our task's hardware requirements. For instance, in our Get Wikipedia entry task, we could notch down the CPU requests and limit to 2 units, and maybe dial back the memory to a modest 2 GB. Honestly, we probably don't even need 2 CPUs, a mere 1 unit might suffice. By specifying our CPU and memory needs like this, we're making more efficient use of our computational resources. And lastly, let's navigate to the Kubeflow documentation, specifically the pipelines documentation and Python SDK reference, where we'll notice a gem of a component dedicated to accelerators. Meaning, if a task can be accelerated, we can conveniently tap into the power of GPUs within our tasks. So consider that we need a single GPU, but remember that we must also specify the accelerator type. Alright, so we have our Wikipedia entry tasks here. We're going to deal with this failure in just a moment, but let's show how we can change the resources. So again, if we view this, we're using default resources. Now let's revise that and see how this changes.
Can't stop working with that GPU. Got the numbers crunching algorithms new. Can't stop running all them crazy Kubeflows with the tensor cores on deep learning nodes. Can't stop streamlining that AI scene. No delay in computes, got to be clean. Can't stop optimizing the model's core, cause tonight this machine's gonna learn some more.
Now, these more unusual, smaller, or bigger tasks may require a little bit more time to boot up, but note that now we're only using 2 CPUs, and we've also got a T4 GPU that we're using. Now, of course, this is pretty silly to be applying a GPU to a task that's just fetching some data from Wikipedia, but it showcases the concept. Let's go ahead and capture this in our notes on tips and best practices here. Alright, and with just a few minutes, we've completed that task again with that very custom hardware setup. Now we can say that qualitatively, we've seen a little bit of a pattern with these setup times for our tasks. Specifically, larger and more unusual machine types tend to take a little bit longer to provision. Alright, for our next tip, we'll use the fact that we have a failure here to kind of showcase a concept. The problem is we've got a 401. We have an invalid API key for our Claude task. Let's go ahead and get an API key to use from the Anthropic website. And then we'll weave that into our script. Worth noting, the only modification we've made is in the translate task of our pipeline. The rest, like our Wikipedia task, remains the same. Now, if we revisit our pipeline and ignite it, we get to capitalize on caching. There are 2 layers of caching that we need to delve into. The first layer resides at the pipeline level, where, with advanced configurations, we can enable caching if we've already completed a step. Alternatively, we can disable caching entirely, causing tasks that were completed previously to be carried out again. This caching aspect is a blessing for larger pipelines, especially when we're debugging. We don't need to run the pipeline in full each time. The caching feature is a game changer for that. Let's witness the caching in action. The baseline caching status remains unchanged at the pipeline level. And when this pipeline bursts into life, it should reveal the Get Wikipedia entry task as a cached item. Look, just as expected, we've got that task cached, smoothing the debugging and development process. Let's highlight that there is a way to modify caching options for a certain task discretely using the Enable Caching parameter. If we wished to never cache, say, the translate step, we can make that call. And now on to the next nugget of wisdom, which is really about using the artifact system. Let's head back to our run here and explore these cool artifacts that we've been creating. They provide us with automatic metadata and cleaner task definitions. So when we get the Wikipedia entry, for instance, and click on that artifact, we can just check out the text from that specific pipeline run and have that at our disposal. The pirate stylized rendition of that Wikipedia content is also an artifact that we can examine in the cloud storage. And yet, as we explore the documentation, we see that there are standard, generic machine learning artifacts in addition to more specific artifacts. We can have things like HTML, Markdown, metrics, key value metrics, as well as machine learning models and all sorts of other interesting artifacts. So our tip here is to use the artifact specificity type that makes sense. The importance of this lies in the intelligent automation that comes bundled with it, like lineage tracking in the metadata. This is really great for ML ops and proper design of experiments. Alright, that was tip number 6. Our next trick, closely related to artifacts, involves exploiting the intelligence of artifact details in crafting your pipelines. Let's illustrate this by printing our entry path and URI for our Claude translation task. Alright, so now that we've unveiled the secrets of artifact details, you can already start seeing the magic here. This artifact system enables us to effortlessly use an automatically mounted Google Cloud Storage bucket for easy writing while automatically crafting these paths for us. Look at this, here's the path and this is the URI. Therefore, in our scripts here, all we have to do is simply open up the files, even though we're navigating the realms of cloud storage. Indeed, this holds true for our inputs as well as our outputs. When the pipeline finally leverages these artifacts, it resembles a local directory since we're once again mounting the Kubeflow bucket as a directory called GCS. Now, a rookie mistake is to see things like entry URI and to leverage the fuse mount while replacing the string expressions in our pipelines. Mark my words, you want to avoid that mess. The avoidance includes deploying the artifact system instead of passing strings around and making sure that you know both the input and output properties are there. And our grand finale tip is tied to parameterization. We've implemented parameterization at both the task level with task arguments, as well as at the pipeline level. This pipeline blueprint is fine-tuned with the concept of parameterization so that without any dreadful recompiling, we can redeploy the pipeline. Envision wanting to add flexibility by letting the language be user-specified. We'd ensure a default is in place, but grant the user the power of specification when they dispatch the pipeline. Of course, we'll still need to make sure that our component tasks get the new specification. As we venture forward with our enhanced specification, we're in for a wave of flexibility here. Moving on, let's peek at the next page where we now find language preloaded with a sensible default value. And now, of course, that'll be transferred to the component. For our 8th tip, remember, injecting reasonable pipeline and task parameterizations and including default values whenever possible is key. A bonus nugget of wisdom here is the concept of using storage systems to house your pipelines and components, specifically the reusable ones. For those in the Google Cloud sphere, you can waltz into the artifact registry, create a repository, and set up your very own Kubeflow pipelines repository. Imagine being able to push and pull your master-crafted assets to this consolidated hub. That's a game changer. Keep in mind you could equally disperse your tasks and pipelines to different storage platforms like Simple Files or Git repositories. As an illustration, when we take a gander at this components page, we spot options like loading from a URL. Leveraging repositories for your components can facilitate reusability and ease of maintenance. And there you have it. We'll wrap up for now. The code and diagram file will be provided in the video description for your convenience. Thank you very much for watching, and please enjoy responsibly.